Okay, let's go on. Wait, who turned the air conditioning off? It's on. It's on. It's on. Okay, so everyone understands the difference. The struct is the normal way of doing it in C. And the annoying thing is you have to write the word struct every time you want to create a new element. So to avoid that, we have a type def. And now we can write element user. And basically, I'm just defining that there's a type called element. And now it's a real type, the same as integer or a float or anything else. And of course, I have to write the word element here in order to give it a name. You may choose to name the struct anyways. Look at this example. Type def struct fish type. Now, which is the name of my type? Of my new type? Fish type or fish type? The answer is fish type. Fish is extraneous and annoying to put there, but a lot of people in their code, they put it there. I don't know, there's some kind of stylistic thing that you put the name here, and then you put a different name here, and then you use this, and the top name here you never use because you can't use it because it's useless. But I don't quite, maybe somebody will enlighten me about what the purpose of that name here would be. I don't recall the purpose. In any case, float weight, float length, float probability of being caught.
Get it float because it's like fish.
Fish float. You caught it.
You caught it, get it, caught it, fish.
No.
That's pretty good.
Nobody fell into my trap.
Get it? Nice, good. Don't fire it.
All right, as long as the network will be good, we'll continue.
Well, that previous one. Yeah.
Okay, a feature of C99. So here's a feature of C99, which is kind of weird. It's called designated initializers. Isn't that a nice word? I just tell somebody, do you know about, what do you think about, it's like if you meet somebody, a friend of yours who studied computer science in like Techniel, and ask him, what do you think about designated initializers? Are you in favor of them or against them? And then ask him what's his favorite type of address binding? Given the following structure, struct point int a int xy. So this is a structure, right? We're defining it. We didn't create anything. We just defined it, right? Now, everybody agrees with me? How would I normally create a new one of those? Well, according to this slide, I have to write struct lm, struct point, and then the thing. So here, struct point p. And then I have to give it its values. Now, normally I would write like this, struct point p, x value for the x, and y value for the y, whatever value I want to put there, like 7 or 10.
Why is there a dot before the y?
So wait a second. So that's the normal way of doing it. This is the designated initializer way. You write dot y, and what you're saying is, it's like saying this. It's like in C++, but you learn in C, you learn in C++ this, right? You learn this arrow or dot, right? Everyone remembers that? You learned C++, right?
Yeah.
You learned this arrow, this dot. When you use this arrow, when you use this dot. When did you use this? You always use this.
Dereferencing the using it as a
Are you
pointer to the object or using it as the object?
as the object? You always use a pointer? He's saying you always use a pointer. Maybe I don't remember correctly.
When you keep this up.
When you do this, when you're
No, there's when it's a pointer, then for sure use an arrow. I mean, maybe you don't on this. Do you ever use it? It could be. I'm thinking of Java. It gets a little bit confusing, but what else? It's like the dot operator of with this. So you say, or the arrow operator with this. But here's a dot because it's a pointer. You see, it's not. This thing is not a pointer. It's not a pointer. It's an integer. So anyway. The kids are, I write dot y, and then I can assign the value, and notice what I can do here, I can assign the order in a reverse order. This is order is reversed, first the y and then the x, I can't do that in the old way. So it's basically just a way of being clear, because this kind of definition is not so clear. If I write 7 and 5, in order for me to understand this line of code, what do I have to do? I have to go back to the file where the structure is defined and see what x is and what, you see which is first and which is second. You see what I'm saying? So that's like very annoying, because it could be in a different file, it could be in a header file. I could have some header file that has struct defined, or some other file, and then I don't know whether to put 7.8 or 8.7. So here I don't care. I just write dot y, and I know there's a y there, but I just don't know what the order is. So I just write dot y equals whatever value I want, and dot x equals whatever value I want. So example of constructing a struct instance. So here we go. Type def struct called point. And notice, all right, I use strike def, and now I can just write point. Oh, this is actually, I'm using a function now which returns a value of type point, and it's called point new, or a new point. Int x, int y. So it takes two parameters, and now it declares a pointer. It declares a point, because every point, right, is on the graph on a Euclidean geometry as an x and a y. So I can say point a dot x equals the x that I got. Now, why can I do that? A dot x? Well, it's the same as what I did over here. Dot x. I could have done. It wouldn't make sense to write p dot x, because it's obvious that it's p, but I could have written it. But here I write point a, and now I refer to the a by its dot operator. So basically, I have dot operators now, but they're called initializers. Designated initializers. Okay, and then a dot x, a dot y, return a. Now, is this a problem? Remember, I declared something, a will go out of scope when this function returns. Is there a problem of returning a?
No, it makes a copy.
Right, it makes a copy. What would have been a problem if it had been a pointer? Right, but this is fine. It's going to make a copy. A will go out of scope, but a copy will be returned, and the values will be there. But at first glance, this might seem like a problem. You've declared something, then you return it, but it doesn't exist. So it will be fine. We're obviously only touching the surface. Obviously, our focus will be C as a programming language tool for system calls, not necessarily for all these intricacies, but I want you to know the ones that I showed you. If you need to learn about any function of the language, features of the language, use this as a manual guide. I found this to be a very good guide. There's lots of guides out there, lots of people put out guides. I looked for what I thought was good a few years ago, and this one is what I found. I thought it's very clear, no extra. Sometimes they have like too much, it's like written in a very technical style. And this is written in a normal style, and it's not extra information, not too little information. Okay, now we're on, so that's now you know C programming, like the basics of the language without relationship to Linux. But now we have to get into compiling on Linux. Now, how do you compile a program up to now? Well, I don't know if you did this already, but normally you were in Visual Studio and you just typed like build, and then run. And you don't know what's going on, you're just clicking buttons. So actually what you're doing is, what you have is what's called a IDE. IDE stands for Integrated
Development Environments.
Yes, development environment. Why is it, what does that mean? Development environment means for programming. Integrated means that you integrated in it other programs. For example, a compiler, a debugger. So this is just the compiler raw, just that part of it that does the compiling. Once you have a program in C, you must save it to a file ending .c. The file must end .c. Really, theoretically, it doesn't have to, but the compiler will reject it. This is the name of the compiler that I want you to use is GCC. There are other compilers, and you can install them on your Linux. but you have to install GCC. And then you write the file name and you hit enter. And it's just like all the other commands that we learned in C in Linux. That you type like WC file name. It's a program called WC that runs on a file name. Here we have GCC, which is a program, runs on a file, needs a file. If you type GCC without file.c, then it'll say like, where's the parameter? I'm missing a parameter. Now, since it's just like anything else, it has flags, minus, and it starts with a minus sign. So you've got a flag called -o, which tells me that I want the name of the file you produce, the runnable file, the executable, to be called whatever I write after the -o. So in this case, I wanted it called file. If I didn't do that, if I just did it the first way, it would have made an executable called a.out. And it would always be a.out. If I wrote 25 programs, it'd all overwrite the a.out. So if I compile 5 programs, I'd only see the last one as the a.out, and the other ones I would have lost their compiled version. Of course, the original source code would still be there. By the way, if you want to run Linux, I mean, you could download the source code of Linux and then compile it with GCC, and then you have a compiled version of Linux, which you could then run on your computer. Or you could just download it already compiled. But let's say you want to take the source code of Linux and change it in some way. So you could, and then compile it, and then run it yourself. It's no mystery. It's not like you have to download the executable version of Linux. Another useful flag is -w, big W, all, with a colon. This will check not only for errors, but also for all kinds of warnings like unused variables, what you may have heard of is called, what's that called when you have a problem in your code which may or may not be a problem? Or a smell. Called a smell. What?
Odor.
Odor?
Yeah.
It's called a smell. It's called a smell, and it means that I smell something bad here. If there's a variable in your program that you never used, sounds like there's a mistake here, because if you declared it, you probably were going to use it, and now you're not using it, so maybe you forgot to do something, maybe your program doesn't work. So it's not going to actually not compile. I could write I could declare a lot of programs that never, and a lot of variables and never use them. But so your normal compilation will not tell you, it's not an error. Now, a lot of companies in the world require your program, when you work for them, they'll say only compile with the -wall flag. And don't, and it has to come out clean, which means when you do the compile, you hit enter and it comes out, there's your program, and that's the name, it says it finished. No other messages. If it gives you any warnings, even with the -wall flag, then fix it. Because there shouldn't be any warning. You should not ever have a warning in your program, even if it's not a serious warning. Okay, now another topic, which is something you may know. Have you learned how to combine programs together? Like if you develop, like a lot of times your program, you're writing a large project and you don't want to have it in one long file. In fact, many people say that no single file should be more than 1 page long. I shouldn't have to scroll through your files. Now, people take this to an extreme, and they have short little files. I would say that even 2 pages is okay. Even 3 pages is probably okay. But I'm saying in a real company. But a lot of people say no, a file should not be longer than 1 page. So you have to be able to put them all together and compile your program. You have this file, this file, and this file, and together they make a program. So how do you do that? So here's an example. I have a main. I just made the shortest example so that it's simple for you to understand. Here's a short main. And all it does is call a function called print hello. But print hello is not anywhere defined in this file. So for that, I have a separate function, a separate file called hello function. Because it really should be called hello functions. Like whatever functions that would be in hello, I'm going to put them over here. And I write over here my function, my print hello. It takes a void, by the way, you don't have to write this, but it's good manners to write void here. So that person knows that you didn't forget a parameter. That you didn't, to tell it clearly, I don't want a parameter here. And it returns void. And then I write print hello make files, or hello files. Return. So here's my little function, and I want to combine them together. Notice, so what I first of all have to do is have a header file, which kind of in other words, theoretically, you would say include hello function.c, and that should be enough. Why don't we do that? We could just write include hello.c, and then to go over to this function, and then we know to get this file. Well, I don't think you can do that. I don't think you can include a C file. What you can do is include a header file. So what happens like this? I include a header file, which is .h, and then I write the definition of the function there. You know what this line? Anyone know the technical name for this line? There's a technical name for that line.
Declaration.
No. Function prototype is false. Technical term for that line is the functional prototype. The prototype for the function. And it shows you the type of the return value, the type of the parameters, and the name of the function, followed by a semicolon. Functional prototype. Type it in your Google. And now when the include runs, now watch what happens like this. If I would just run this function, this program, it would compile. Because what does the compiler do? He checks, he says, is there a function declared called my print hello? And he would say, what's its sorry, he would compare between this and say, all right, how should I say? Let's say I wrote my print hello with a number here, 7, put a 7 in there. So the compiler would say error. How does it know there's an error? Because it would detect that the parameter list is incorrect. It should be void. It shouldn't have a 7 there. How does he know that? The only way he can't know it from this file, he can only know it from looking at this file, which tells him that it has to be void. So in order for the compiler to give you an error message, like you're using the function wrongly, you put in the wrong parameter list, or the name is wrong, he has to have the header file. But that doesn't mean he can run the function. That's what you need this file for. This is the actual running. But this just allows him to know that the function is being used correctly. Now, what's going on over here? Here I say include standard IO, input output. Why do I do that? That's what printf will work. Printf is in a standard library called stdio. And I also have to include hello header. Why? Because why don't I include hello header? Because why? Well, he included hello header. Hello header. Not sure about that. I don't know exactly why. I think I do have to, but I'm not sure exactly why.
Stop you from declaring it twice. Function the same.
Oh, so that if I compile this, so let's think of it. So that if I compile this, you can also check that I used the function correctly. But even that this matches that. It's just to make sure that this matches that. That I didn't. That I could have written here a void and here int 7, hint A, and then it has to know that I have to match it. Okay, so now that I got this all set up, I can do the following command: gcc -o to define the function, the name of the program that I write, that I create, called to hello, and then I write the 2 C files, but not the headers, because the headers are included. He knows how to find a header. Now, the only thing is, where should he look for the header? He should look in the current directory. So for that, I have to tell it this -I minus I dot. So let's see what it says. This compiles the two C files and names the executable hello. The dot, the minus I, capital I, is included so that GCC will look in the current directory for the included file, the header file. In other words, it's enough to, I can't just say hello. Why didn't I have to tell it where to look for the stdio header? Because it's in a standard location. Theoretically, I could put my header file over where that header, studio8.h, is sitting, and then I wouldn't need to do this. But if I want to keep it local, then I have to tell it, look here. And there's certain default places that it looks, but it has to also look here. Okay, so now that's how I would compile it. GCC minus O, hello function.
Does it matter if it's hello.c or hello function.c first?
I could write GCC and then not write the dot minus O hello. And then write the hello C and the hello this and the minus I, and then write minus O hello.
In between hello.c and hello function.c. Does that work between those two matter?
Yes, definitely. 100%. Good test question. Okay. Create an empty direct. So here, now I want to show you something else, and then we're going to combine the two things that we just saw. So another thing I want to show you is a make file. Did I? That's it. Oh, wow. Okay. So look at this. I can make a file called a make file. And a lot of people, when they compile programs, they like to use a make file. But before we learn how to compile programs to make file, let's just learn how a make file works in general. So in general, I say like this: say hello, colon. And then I do a tab, must be a tab here. Echo hello world. Now this has to be in some kind of directory that the only thing in that directory is this make file. I mean, not the only thing. There's no other make files. Sometimes you have many make files and they conflict. You can't have more than one make file. So as I say, create an empty directory called my project, containing a new file called make file, capital make or lowercase make. Both are acceptable with this content. Say hello, colon, echo hello. Now run the file by typing inside the directory project, my project, the word make. And make is a program, which is pre-written program, which looks for a file in the current directory. That's why I have to be in the same directory as the make file. It looks for a file in the current directory named make file and runs it in a certain way. What does it do? It sees the echo hello line, and it first prints out what it's going to do. It tells you what it's going to do, and then it does it. And it says hello world. So as if I would have a grep here. Let's say I would have a grep, some regular expression on file, and then I would say, it would say grep regular expression on the file, and then here I would see the output of that command. I would see all the data in the file that matched the regular expression. You guys learned about grep in my video.
Yeah.
So that's basically it as far as a make file. It's pretty simple. Now, why do we have these things here? This is, in the above example, say hello behaves like a function name, as in any programming language. But it's called a target. If I have multiple targets, so I could have say hello, say goodbye. I could have some other thing. And then if I have multiple targets, I can select the target to run by writing make target. Example, make say hello would run this. But if I had another one, let's say goodbye, then I could say make say goodbye. By default, if you just type make, it runs not all of them, but just the first one. Whatever is the first target will be hit only. So here's an example, echo stom, ls. So stom and stom1. Notice that I have many things that I do. I do 3 echo stom, ls minus l make star echo done, hello goodbye. So I can run either of these sets of procedures. I can write a whole set of procedures here, right? By typing make stom or make stom1. Now I can go to my make file and I can put a rule like this. Hello make file, and then write hello.c, hello function.c. And I put the two programs that I'm interested in. And then I say the actual command that I want. So wait a second, my target is still hello make. But I've added something here which I didn't explain yet, but bear with me. GCC, hello, hello, hello C, hello function C. Those are my two functions. Put this rule into a file called makefile or makefile, and then type make on the command line. It will execute, and it will execute the compile command. So you have written it. Make with no arguments executes the first rule. Furthermore, by putting the list of files hello.c and hello func.c on which the command depends on the first line after the colon, make will know that the rule hello make needs to be executed if any of those file changes. Without this, make will think nothing has changed and therefore won't recompile. A little bit confusing the way I wrote it, but basically the idea is we're trying to get that feature that you have in Visual Studio, where if one of the files hasn't changed since the last build, then it won't build it again. If I type build and run, if I hit build and run and it's already built, it just will run. It won't build it twice. But if something changed, if I change one letter, then it will run it. So you could do the same thing with a make file, and therefore it's faster, because if your program is like millions of lines long, then the compiling will take minutes. So you don't want to wait minutes. So if you didn't change anything. In fact, by the way, that's another reason why you want to divide your program. Imagine you had one file that was 1,000,000 lines long. So any one change in the file, you'd have to compile the whole file again. But if you have a single executable created from 1,000,000 different files, or from 10,000 different files, each one with 10 lines, then 100 lines, then only if you change only one file, it'll only compile that one. That'll only compile that file, and all the other files won't have to recompile. It maintains a version. It could maintain a version of the files before it combines them.
So you still have to recompile it in one file changes.
There's something called the linker. First compile goes on each file, and then the linker. I'm sorry, you have to do GCC minus C. If you do GCC minus C, then it compiles without linking, and then you'll have a version of each program separately. Anyway, that's the basic idea. I'm not really explaining all the details, but the basic idea is that you could theoretically compile each of those things and then keep them. And then when one changes, just can recompile that one and then relink it all together. And that would be an advantage of not having one program with 1,000,000 lines. The linker will still have to link everything together. One very important thing is there is a tab before each line here in the after the target. There's also flags, like I can define, not flags, variables. I can define variables like CC. I can define a variable, or it's a macro. I can say CC equals GCC, and C flags equals minus I my dot. So now I can write my line like this: variable CC is my compiler, and flags are my flags. And what does this give me? That I can change my compiler at will once, and for all the rules, I may have many rules or many targets, and all of them will be changed. I can change my compiler as I wish. without having to change the lines in the code. Just like any variable. This, I have to, truth is, I have to a little bit clarify this, this is, this should be changed to a C. Okay, wait a second, that's it, for that lecture. But we have some time, so we'll continue. Wait, let me look here, let me stop the